before I start, just let me modestly pay tribute to a great poet and singer, Leonard Cohen, who passed away a few weeks ago. The work, what I will present you is not my own work, but rather a compilation, I would say, of the preparatory work made by the JWST team to prepare the observations with this new mission. Okay, so the James Webb Space Telescope, so that's a big NASA project with a large contribution from Europe for one instrument and a half, and so Canada and the launching by Ariane 5. The launch will be now in 2 years from now with a large primary mirror. I'll come back on that. A lifetime of 5 years with an objective of 10 years, in fact, and a large spectral range, which is really something new. And so with imaging and spectroscopic capabilities. The orbit will be at the L2 Lagrange point, so that there will be low radiation from the Earth, and this allows to point any location in the sky with the sun in the back. So the deployable telescope, that's really a big challenge, also a $10 giga challenge. The largest telescope ever launched in space compared to the Hubble primary telescope there. It should be accommodated in the fairing of Ariane 5 so that it has to be deployable and segmented. But despite of that, it will have an excellent image quality because it will be diffraction limited beyond 2 micron, and it will be, of course, a cryogenic system since it is mainly devoted to work in the infrared. So there are 4 instruments. I will not detail them, just to mention that they give both spectroscopic capability, imaging capability for those different instruments, and MIRI especially will be devoted to the 5 to 28 micron range. So the observational capability I mentioned, so imaging, spectroscopy, of course, with different possibilities, including slitless spectroscopy and so on. And you notice especially the devices of coronagraphy, which will be especially useful for planet studies. The sensitivities, there will be a big step thanks to, of course, the large diameter of the telescope. So compared to the previous mission or ground-based instrumentation, and for instance, compared to Spitzer, at least a factor of at least 15 in the thermal infrared, and also large factor compared to what can be done with large telescope on ground. The capabilities, so we see the Exoplanet program, which should represent about 1/4 of the time that will be dedicated on the JWST. So first, of course, the ideal wavelength domain, if you consider, for instance, the emission of planets like those of the solar system of hot Jupiter. So with NIRCam here and MIRI, 2 of the instruments, you largely cover a very useful range, I would say. Second, an excellent angular resolution, for instance, compared to Spitzer. This is an image of Spitzer of this famous disk around the Fomalhaut here at 24 micron. This should be, that's a prediction, of course, a prediction how it might look, the image so given by MIRI at about the same wavelength. So And then the high contrast imaging, which that will be made possible through coronagraphy. I will not enter in detail of coronagraph. Coronagraph are not, that's just the device that allows to suppress most of the light of a star so that you can reach the light of the planet. They are sophisticated device, not just a black spot. Okay, so I will not enter in detail, but just to illustrate you, for instance, for the coronagraph on Mary, which looks like that, what we call four-quadrant coronagraph. Now, okay, if you move a star on this coronagraph, you will see that's real images obtained, no, of course, not on a star, but on a source. Okay, can you make the movie? And you will see what happens to a star that will cross this coronagraph. So you see it disappear almost totally. And so if there was a planet somewhere, there is a much better condition to observe a planet. So those different coronagraphs will be used in the JWST. Okay, what else? Spectroscopic capacity, I already mentioned that. Just here to mention that the two do different wavelength range and all the different capabilities. There is a variety of capabilities in terms of spectral resolution, from very rather high resolution to modest resolution, of course, depending of the brightness of the source and the one that will be the best suited for those observations. So exoplanets. The main goal, of course, will be the study of atmosphere, to learn more about the nature of exoplanets, their diversity. We heard, of course, of that with the talk by Alain. And then understanding, of course, the physics and chemistry at work in those atmospheres, and concerning also planet formation through the study of metallicity, C2O ratio, and ultimately searching for possible biosignature, for instance, ozone. So the molecules that will be accessible with JWST, though there are plenty of them in the different wavelength range, with some which are of special importance, ammonia, of course, methane, CO, CO2, H2O will be accessible. So the typical program that will be made with the JWST on the exoplanet topics will be first coronagraphic imaging of young planets. I mean young planets because that's, as Alain explained, the only way really to reach the thermal emission, the proper thermal emission of those planets, which are still rather hot because they are still contracting. So around young stars, of course, and nearby also young M stars. And it will be possible to reach much lower mass than what is done presently with, for instance, the Hubble Space Telescope. And so access, of course, to the atmospheric composition, physical properties. Spectroscopy of young planets. In a few cases, it will be possible to make direct spectroscopy of those planets when the distance will be large enough from the star. Coronographic imaging of debris disk also is an important part of the program, and how, for instance, the planets can curve the disk, also the interaction, the composition, the structure of the debris disk, and finally, a very important program also, which will be the transit spectroscopy of hot or warm or even temperate planets, so planets which are not resolved spatially, but by doing some differential spectroscopy. So let's enter in a few details. For instance, so one of the big plus of the JWST in terms of coronagraphy is its stability, because it will be extremely stable in terms of optical quality. So even if they are speckles, they will be stable. So it will be possible to subtract an image of a reference star so that you can really remove the residual speckle and reach very low, hopefully very low planet mass, typically of the order of 0.1 Jupiter mass, which is not the case at all for the present time. This is an illustration of what in simulation with MIRI, for instance, of the this famous system. So those coronagraphic observations, there are plenty of filters that are of special scientific interest on different lines, as so methane, CO2, CO, H2O, of course. And so there is this interest of the broad wavelength range, and so also, of course, access to lines which are otherwise blocked by the Earth atmosphere. And so, for instance, on MIRI, there will be specially chronograph on this NH3 line at the different wavelengths, so that will be possible to have a precise estimate of the temperature, of the abundance of NH3, for instance. Coronagraphic imaging of debris disk also. This is of course not prediction, but just this detected recently by the instrument sphere at the VLT, just to illustrate the very diverse diversity in the disk that can be observed with spiral structures, with voids, with different really complex structures. And so this is also that's a very important part of the program, because this will be crucial to understand really the planetary system formation, evolution, and how, as I mentioned, the planets can curve those debris disk. Okay, direct imaging and spectroscopy, I would say, if the angular distance is large enough, it will be possible. So typically beyond 2 to 3 arcseconds, it will be possible to make direct spectroscopy of planets. And this is, again, of course, I just show simulation, but realistic simulation, taking into account now the non-performances of the instrument, of, for instance, a MIRI LRS spectrum, and this is really the signal to noise which will be obtained. So a really large signal to noise on the planets such this one, which is say a rather hot planet, but even on colder objects such as JJ54b, for instance. Again, the signal to noise that will be reached should be extremely good. Now the spectroscopy of transits. So Alain already explained how this works. So this is the case of exoplanets which are not separated by the optical system. So you have hot planet, generally hot, but they can be also just, I would say, warm or temperate, hot planet close from the star. And so through differential measurement, either through a transmission through the atmosphere of the planet when during the transit, or when there is an eclipse, it will be possible so to obtain the spectrum again on a broad range, including so up to 28 micron in a certain time. And provided that you have a very good signal to noise, it will be also possible to make 2D maps from the ingress, just the monitor of the ingress and the egress of the planet during the eclipse, so that you may access to information, spatial information on the exoplanet. For instance, if there is a hotspot which is shifted due to the some winds or some movement in the atmosphere of the planets, this should be possible. Okay, spectroscopy of transits again. So we know that that's already, of course, possible. For instance, using the Hubble Space Telescope, but here the domain of wavelengths which be much larger, and of course the signal to noise also should be much better. So a few examples of simulation with the JWST, of course, different cases. For instance, an hot Jupiter, in the case where there are clouds or no clouds, okay. Or in the case of a cool super Earth, and this is for transit and for eclipse. So the emission spectrum of exoplanets will be available still, for instance, for hot Jupiter or cool exoplanets. Of course, the noise will be larger in that case, but still a lot of information will be available. An example with NIRISS, one of the instruments, how precise will be. This is, of course, a theoretical spectrum. We can see the data points on this with the noise which is expected just after 6 hours of observation with NIRISS of this object. Photometry of transit, even on super Earth in the habitable zone. This is a prediction for a few objects which are not already existing, but we expect that tests will detect that kind of object, so that of planets in the habitable zone. It will be possible here not doing pure spectroscopy, but just differential imaging using the Myri filters, with a CO2 strong line that should be detectable. Another example, biomarker O3, the ozone. Also, it is expected. Of course, it will be rather difficult to do that, but to detect the ozone line at 9 microns through, for instance, in this TRAPPIST-1 system with B, C, and D planets, which are really temperate planets. Okay, thank you. And this, of course, requires a lot of transits, 90 transits at least for this planet, for this planet. For the other one with 30 transits, this should be possible. It takes a long time, of course, but it is accessible. And last example, the clouds. This is a simulation made by Benjamin Charney and collaborators, and how here with that kind of simulation using their GCM model, which include radiative transfer and clouds, they were able to explain the HST data. So this flat spectrum in the case of JG1214b, but what they predict also is that it will be possible to detect molecular features even if they are clouds, and also very important, the Mie slope will be the Mie slope due to scattering by those particles will be also detectable. Okay, thank you. So this is just a summary of what I compile as what is expected with the JWST. Thank you very much.